Now that we know how to represent integers in signed and unsigned binary, we should talk about how to do math on those binary numbers. The main types of arithmetic operations we'll talk about include addition and subtraction, along with multiplying and dividing by powers of 2 using bit shifts. It's worth remembering that CPUs contain circuitry for performing lots of arithmetic and logic operations on integer data as well as on floating point data. So the operations that we will be focusing on now and in our study of circuits will be a small but important subset of the things that CPUs can do. The C programming language has operators for performing bit shifts. If we declare a variable of one of our integer types, then we can perform bit shift operations on that value. This operation performs a left shift, indicated by the direction of the chevrons, and it shifts by 3 places. So this is equivalent to multiplying by 2 to the third. Here the chevrons are pointing to the right, and so we are shifting x to the right by 2 places, which is equivalent to dividing x by 2 squared. And any remainders are lost, and so we end up with a value of 3. To illustrate this a bit more precisely, let's think about what's going on with the binary representation. A character is an 8-bit signed integer, and so we have the number 13 represented in 2's complement binary. And when we perform a left shift by 3, we move all of the digits of x 3 places to the left and fill in zeros from the right-hand side. And any digits pushed off the left end are lost. And so this value is 64 plus 32 plus 16, which is 104, which corresponds to x times 8. When we perform the right shift by 2, we are taking the digits of x and moving them 2 places to the right. And since x is a positive number, we want to fill in with zeros from the left-hand side. And we lose 2 digits off the right-hand side, leaving us with 2 plus 1, so the result is 3, which is the same as integer division of 13 by 4. But as we talked about in the previous video, filling in zeros on the left end when we shift things to the right doesn't give us the right answer if our original value was negative. So let's think about another right shift example where that makes a difference. If we take this 8-bit value and right shift it by 3, we would like for the result to be mathematically equivalent to having divided the number by 2 to the third. So what is this number divided by 2 to the third? Well, that has a different answer depending on the data type of this 8-bit value. If this was a char variable, then a char is an 8-bit 2's complement integer, and so this is the value -96. But on the other hand, if this were the value of a variable that has type unsigned char, then that would be an 8-bit unsigned int, in which case the leading one would mean positive 128 instead of negative 128, and so this would be the value plus 160. And so, if we are trying to do a right shift that divides by 8, we need to get a different result if this means -96 versus if this means positive 160. So in the first case, we want to get a result of 160 divided by 8, which should be 20. And in binary, that corresponds to filling in zeros when we shift to the right. Whereas in this case, we want to get a value of minus 12, which corresponds to filling in ones when we shift to the right. And so, because this binary operation needs to give us a different result based on the data type of the variable, the CPU actually implements two different kinds of right shift. One type of right shift works for signed numbers, and one works for unsigned numbers. If the data that we're dealing with is an unsigned variable, then we want to fill in with zeros no matter what the leading digit was. This corresponds to the logical right shift operation. Whereas if the variable that we're dealing with is a signed data type, then we want to fill in with zeros if the leading digit was 0, or ones if the leading digit was 1. This corresponds to an arithmetic right shift. And so, when we write a C program that uses a right shift operator, the compiler will need to pick a different CPU instruction, either logical right shift if our variable was unsigned, or arithmetic right shift if our variable was signed. Now let's move on to addition in binary, and as I've indicated here, subtraction will turn out to be just a special case of addition. Let's start again with some example C code where we all understand the operation that should be performed and think about what's going on with the binary representation. For these operations, we know exactly what result we expect. So let's take a look at what's going on with the binary values and see how we get there. We've already seen the number 13 in 8-bit binary. And the number 5 is a 4 and a 1. And now we can add them in much the same way we learned to add multi-digit numbers in grade school. We start from the right-hand column, and we add up the digits in that column. 1 plus 1 is 2, but in binary, 2 is represented as 1, 0. So we write down the 0, and we carry the 1. Now we have 1 plus 0, so we get a 1. 1 plus 1 is 2, so again, we write down the 0 and carry the 1. And 1 plus 0 is 2, so we write down the 0 and carry the 1. 1 plus 0 gives us 1, so we have no carry, and the rest of the way we'll get zeros. So, we all know how to do this operation already, and actually the binary version is easier than the version that we've all done before because we're just adding zeros and ones, and the result is always going to be between 0 and 3. And we can verify that we got the result we wanted. We have no 1s, a 2, no 4s, no 8s, and a 16. So 16 plus 2 gives us 18. Which was the answer we wanted. Now let's think about how to do subtraction in binary. We could also write it out like grade school subtraction, but that would get tedious because we would end up having to do a lot of borrowing. Instead, we can turn our subtraction problem into an addition problem. Clearly, we could add -5 instead of subtracting 5, and we know from last time that to go from 5 to -5, we need to flip all the bits and add 1. So let's set up our addition problem. So now we want to add -5, and we could, in principle, figure out the value of -5 to fill in here, But there's an even easier thing we can do, which is to separate out the two steps of flipping the bits and adding 1. So what we'll do here is write down 5 with all of its bits flipped. In C, the tilde operator is a bitwise negation. So relative to our representation of 5, all of the zeros will become 1s, and the 1s will become 0s. So we flipped all of the bits, but to get -5, we would need to flip all the bits and add 1. So what we actually wrote down here was -6. And so if we're adding x plus -6, we'll be off by 1. We need to add 1 more. But the handy trick is that we can pretend we have a carry coming into the first column of our addition. And by including a carry on this column, we will add 1 to the overall result, which will be equivalent to having added -5. So now we perform our addition. 1 plus 1 gives us 2, so we write down the 0 and carry the 1. 1 plus 1, we put a 0, carry the 1. 1 plus 1, we get a 0, carry the 1. Now we're adding 1 plus 1 plus 1, so that's 3, which is 1, 1 in binary, and so we write down a 1 and carry a 1. Now we get 1 plus 1, so 2, 0, carry the 1, 0, carry the 1, 0, carry the 1, 0. And now we have a carry, but that carry goes out the end of our 8-bit number and gets lost. And the result is a positive number. We have 1s, 2s, 4s, 8s. So we got positive 8, which was exactly the result we wanted. In a moment, we'll talk about overflow, which is the cases where the binary arithmetic gets the answer wrong because the answer was too large in magnitude to be represented in our fixed bit width. But to do that, it's going to help us to name a couple of components in these addition problems. The carry in is the carry value that we put on this first column, and that value will be 0 in the case that we were originally doing an addition problem, whereas it will be 1 if our original problem was subtraction. We also have a potential carry out of the last column of our arithmetic problem. And sometimes the value of the carry out will help us identify whether we got the right or wrong answer. So, what the heck am I talking about getting the wrong answer? Let's do another 8-bit example, and we'll start by adding two negative numbers. This is an addition problem, and so we don't have a carry in. And so now we can compute the sum of these two negative numbers. We did have a carry out the end, but let's see if we got the right answer. We wanted a result of -45, and what we got was minus 128 plus 64, so that's minus 64, plus 16 is minus 48, plus 2 plus 1 is minus 45. So this gave us the right answer. But what if we had done this same addition, but these had been unsigned integers instead of signed? In that case, this would be the number 236, and this would be the number 231. And if we add those, we get 467. And this is not an unsigned representation of 467. This, as an unsigned integer, is 211. And so if these numbers that we were adding had been of type unsigned char, then the answer that we got would have been wrong. Why is this answer wrong? Well, the result that we wanted to get is larger than 255, which would be the biggest number we could represent in an unsigned char by setting all of the digits to 1. And so there's no way that we can represent this answer. And that means that when we did this arithmetic, the carry out that went out the end was actually another digit that we would have needed in order to represent the correct answer. So this is an example of arithmetic overflow. An overflow happens specifically because we have to use fixed width representations of our integers. And that means that when the circuitry performs an addition operation, sometimes the correct answer to the problem we asked it to solve will be outside the range of possible values for our fixed width integers. And in that case, no matter what the circuitry does, the answer that it will give back within our fixed width integer must be wrong. But as we saw, whether the answer is right or wrong can sometimes depend on the data types in your program, and the CPU doesn't know anything about whether it's adding signed or unsigned integers. And so, to detect whether our binary arithmetic has given a correct answer or had an overflow, we need some way of checking the information that the CPU actually produces when it performs the arithmetic. So our goal is to figure out how can we detect when the answer to our arithmetic is out of range. And so let's think about, for the different data types, when is the answer out of bounds? And that, of course, depends on the range of values that we can represent in a signed or an unsigned integer. If we have an unsigned integer type, then the smallest value we can represent is all zeros, and the largest value we can represent is all ones. All ones in an n-bit number is 1 less than a power of 2. In particular, it is 1 less than 2 to the n. If we're using a signed data type, then our range of possible values is centered on 0. The smallest number we can represent in a signed data type comes from setting the first bit to 1, that is, the negative 2 to a large power will be present, and all of the other bits to 0. That is, we're not adding any positive values back. And so that value of a 1 followed by n minus 1 zeros is equal to negative 2 to the n minus 1. And the largest value we can represent has a 0 in the first column and 1s in all of the remaining columns. And so that is kind of like our largest value here, except we have one fewer digit to represent it because we set the sign bit to 0. And so our maximum is 2 to the n minus 1 minus 1. And so to detect overflow, we want to figure out how we can identify the cases where unsigned arithmetic went less than 0 or greater than 2 to the n minus 1, as well as cases where signed arithmetic went less than minus 2 to the n minus 1 or greater than or equal to 2 to the n minus 1. Let's look at some examples to try and figure out how we can identify when the result is out of range. We'll start with unsigned addition. If we're using unsigned numbers, then we know that both of the values that we're adding are positive, and we are performing addition, so the result can only get bigger. And so if we're doing unsigned addition, there is no way that we could get a result that is less than 0. And so the only danger of overflow here is going bigger than the maximum value. Let's look at a 4-bit example where that happens. Here we're adding 12 plus 10, so the result should be 22, which is bigger than 15, the maximum we can represent. So we expect overflow to occur, and when we perform our addition, we got a carry out the end that we would have needed in order to represent the value 22. And so the answer that we actually got of 6 is incorrect for the addition we were trying to perform. And so in the case of unsigned addition, having a carry out the end is indicative of the fact that we needed that extra digit in order to represent our answer. For unsigned subtraction, we clearly can't get bigger than the maximum. The danger is that we might go less than 0. And so let's think about a case where the result of the subtraction would be negative, like 10 minus 12. So we put 10 in 4-bit binary on top, and then we take the negation of 12, so that would be 0, 0, 1, 1, and we include a carry in because we're performing subtraction. And now, when we carry out our arithmetic, we get a result which in unsigned 4-bit binary represents 14, which is clearly not the right answer. And so here, when we were doing a subtraction problem, we had a carry in, and then we actually added two numbers. And so if we're adding two numbers, and those numbers are both positive, if we don't have a carry out, then the result is going to be bigger than either of the two numbers that we were adding. And so actually the only way we can get a correct answer is if there is a carry out the end that allows us to get a result that was smaller than the number that we started with. And so for unsigned subtraction, the lack of a carry out is indicative of overflow. And so for unsigned arithmetic in general, doing addition and having a carry out means overflow. Doing subtraction and not having a carry out means overflow. And so if the carry in and the carry out are different in an unsigned arithmetic problem, then we know that there was overflow. For signed numbers, we don't have the same dichotomy between addition and subtraction, because when we have both positive and negative values, we could, with either an addition or a subtraction, end up going out either end of the range. For signed arithmetic, the danger is that we have a carry which messes up the sign column, taking us from what should be a positive result to a negative, or vice versa. One thing that can go wrong with signed arithmetic is that we can add two negative numbers and end up with a positive result. So here we added minus 8 plus minus 2, and we got positive 6, clearly a wrong answer. Or we could add two positive numbers and get a negative. Here we're adding 7 plus 2, and we got negative 7 as our result, which is clearly wrong. So with signed arithmetic, the danger is if we add two negative numbers and get a positive result, or add two positive numbers and get a negative result, then clearly something has gone wrong. What's gone wrong in these cases is that here we had a carry out of the sign column, but we didn't have a carry into the sign column to replace it. Whereas down here we had a carry into the sign column, and we didn't have a carry out of the sign column to get rid of it. And these are the only cases where we can get signed overflow, because if we were to instead add a positive number plus a negative number, then the result is always going to move closer to 0, and there's no way that it will be out of bounds. So when we're doing binary arithmetic, we need to be careful that the correct answer to our problem can be represented within our fixed bit width. And Since we're eventually going to be implementing these things in circuitry, we want a way of detecting the overflow that doesn't rely on knowing what the answer should have been. We need to detect it based on the bits involved in our arithmetic problem.